In October 2012, an experimental flight dropped a human being from an altitude of 39,000 meters. Stepping onto the edge of the capsule, the subject was exposed to an environment that is, for all practical purposes, a vacuum. At this height, the acceleration due to Earth's gravity pulls downward at approximately 9.68 meters per second squared, nearly identical to the force felt at sea level. The near-total absence of atmospheric density is the primary variable that defines the stratospheric drop. This dual-axis chart maps atmospheric density against altitude. Looking at the 39-kilometer mark on the x-axis, the local atmospheric density reaches its minimum, approaching absolute zero. Without air density, there are no physical molecules to push back against a falling object. The upward vector of aerodynamic drag is eliminated. Because there is no drag to oppose gravity, the body continues to accelerate, completely bypassing the standard terminal velocity limits that dictate skydives in the lower atmosphere. Removing atmospheric friction allows the descent to behave as a pure exercise in orbital mechanics. In this environment, breaking the sound barrier becomes possible, because the speed of sound is a shifting variable, dictated by the medium it passes through. The Laplace correction equation determines acoustic velocity by dividing pressure by density. At 30 kilometers, the speed of sound plummets to 305 meters per second. The freefall velocity curve intersects this lowered threshold, allowing the subject to reach Mach 1.25. This exposes a fatal aerodynamic paradox. The exact lack of air density that permits supersonic acceleration also strips away all aerodynamic damping. Without an atmosphere to push against, biomechanical movements are useless. Extending an arm or leg provides no resistance, failing to act as a control surface. If an asymmetry develops in the fall, there is no way to correct it. The body is forced into a flat spin, a violent, unrecoverable horizontal rotation along its x-axis. Driven entirely by its own unresisted physical momentum in the vacuum, the falling mass begins rotating horizontally at a violently high speed. The precise aerodynamic conditions required to break the sound barrier naturally engineer an environment where total, violent loss of attitude control is a near certainty. Once the spin begins, the threat shifts from external aerodynamics to the extreme internal mechanical forces exerted on the human body. A highly specialized pressure suit packed with heavy life support instrumentation unnaturally shifts the wearer's center of mass upward into the mid-thoracic region. This biomechanical model shows the physical reality. The horizontal spin anchors at the chest. The rotation turns the chest into a centrifuge, driving blood volume out of the legs, pulling at cephalad to stagnate in the upper torso and head. Aerospace physiology defines this severe headward physical stress as negative GZ acceleration. This chart plots the mechanical force against rotation speed. A spin of 50 revolutions per minute subjects the head to negative 0.9 GZ. At 75 RPM, the force doubles to negative 2.0 GZ. Hit 100 RPM, and the body takes a sustained negative 3.5 GZ. The sensation of weightlessness vanishes. In its place, the spin generates a localized, crushing high-gravity environment within the upper body, triggering a multi-organ cascade failure. The cardiovascular system is the first to fail. Because centrifugal force pins fluid to the extremities of the spin, venous blood return from the lower body back to the heart effectively ceases. The heart muscle continues its electrical rhythm, firing and contracting, but the chambers are now operating virtually empty. For the contractions, the opposing inner walls of the cardiac chambers slam directly into one another, inflicting acute endocardial contusions. Moving up to the neck, carotid baroreceptors are simultaneously hammered by massive, unnatural spikes in headward blood pressure. Interpreting this pressure as a critical emergency, the autonomic nervous system triggers an extreme vagal response to rapidly depressurize the head. Peripheral vascular beds are forced to dilate. This completely eliminates vascular resistance, inducing profound bradycardia as the heart rate slows to a crawl. Sustained exposure to negative 3 Gs pushes this vagal response so far that it induces complete asystole. The heart entirely stops beating. As the heart fails, a secondary crisis unfolds in the brain. The extreme centrifugal force physically pries open the cranial vasculature, allowing excess blood to pack into the skull. With no venous return to clear the vessels, this trapped blood rapidly deoxygenates, resulting in severe cerebral blood stagnation, local hypoglycemia, and massive tissue edema. Inside a high RPM flat spin, the brain slowly drowns in stagnant, deoxygenated blood, while the heart literally beats itself into cardiac arrest. This extreme hemodynamic pressurization is most visible mechanically in the delicate, highly vascularized tissues of the eyes. This graphic tracks intraocular pressure during a flat spin. The pressure inside the eye isolates, spiking 40 to 60 millimeters of mercury higher than the aortic arch. This surge shatters hydrostatic limits, rupturing capillaries, resulting in gross conjunctival hemorrhage. While the head is pressurizing, the torso experiences a purely mechanical failure of the pulmonary system. The relentless headward pull of the negative G's force causes heavy abdominal organs, like the liver and stomach, to physically displace upward. This mass of shifting viscera crushes into the diaphragm, heavily compressing the delicate pulmonary tissue sitting directly above it. Clinically, this compression causes atelectasis, widespread instantaneous lung collapse accompanied by massive pulmonary shunting. Because the alveoli are crushed flat, pulmonary shunting routes blood through the lungs without taking on fresh oxygen, rapidly compounding the brain's existing hypoxic state. A sustained flat spin mechanically crushes the lungs and ruptures ocular blood vessels, completely cutting off the oxygen supply to a starving brain. The human body possesses strict, unyielding operational limits when subjected to this specific mechanical environment. Clinical data demonstrates that human tolerance to a flat spin deteriorates rapidly once the rotation crosses 80 revolutions per minute, or roughly -2 Gs. At this rotation rate, the extreme physiological stress induces severe vertigo and total operational incapacitation within just 2 to 3 seconds. Aerospace engineers usually solve this physics problem with a simple tool, a drogue chute, which anchors the fall and mechanically prevents a flat spin from ever forming. This visualization demonstrates the trade-off between stability and speed. Left, a drogue chute safely anchors the figure. Right, the figure falls without one. The drogue's drag coefficient caps terminal velocity, making it impossible to break the sound barrier. Pushing the boundary of aerodynamic speed required removing the drogue chute. It was a calculated gamble, prioritizing velocity by consciously accepting a razor-thin margin of survival against massive internal injury. Establishing these precise physiological thresholds defines the baseline safety requirements for modern crewed spaceflight. A catastrophic launchpad abort, or the sudden loss of attitude control while floating in the vacuum of space, will subject an astronaut to these exact same rotational negative G's forces. Look at this pad abort test of a SpaceX Crew Dragon capsule, firing its escape engines to rapidly launch away from a theoretical rocket failure. During maneuvers like this, engineers must carefully design automated thruster profiles and physically align the crew seats to minimize any sustained negative G's exposure. The precise organ failure timelines mapped from stratospheric freefall experiments supply the bedrock data required to establish those spacecraft survival parameters. Before we can build the vehicles that carry humans safely to orbit, we first have to mathematically define the exact biomechanical breaking points of the human body.